Welcome everybody, and thank you to my presentation, Unleashing the Power of Advanced Motor Testing Techniques, Flux, Harmonics, Test Acceleration, and Electrical Noise Immunity. A little bit of a mouthful, but as I like to call it, motor testing Bouillabaisse, inspired by the Beastie Boys. I couldn't really choose one to dive deep into, so we're going to go through just a bunch of stuff that's kind of the state of the art in electric motor testing. Again, I'm Mitch Marks, and I work for HBK. For those of you who don't know, HBK is kind of a monster in test and measurement. So if you can physically see it or feel it, we can probably measure it. Quick agenda. So we're going to look at just some challenging scenarios for motor testing or some state of the art. High-speed motors, drive cycle testing, flux-based controls and torque calibration. Measurement side, everything's from the measurement perspective. Harmonic analysis, torque ripple and NVH type measurements, test acceleration, electrical noise and high voltage, and lastly, just a little sprinkle on HBK. So HBK makes product. This product will be featured in today's examples. We have a data acquisition system, a power analyzer, sensors, and software. We do 5 things really well. We measure electric and mechanical signals on the same timestamp, and they're very well time-aligned. We make really fast and accurate efficiency measurements, so very high accuracy, very quickly and dynamically. Future-proofing, we allow you to expand out or add a lot of channels. We record all of the data and allow you to view it like a scope. And lastly, we offer real-time calculations. So everything we do is in the real time. It can be offered for feedback to a hardware in the loop, to an automation system. So again, we have torque sensors, load cells, current sensors, accelerometers, and more. We have data acquisition systems that have an extremely high accuracy for electrical power. And then we have some really cool software that allows us to do things like mapping in real time, color plots, and then just viewing signals. In most markets, we have local support and training. And again, this presentation will feature data and examples that were acquired using our measurement systems. So into the good stuff. So dynamic power measurements, faster speeds and drive cycles. So we're seeing an industry trend for high-speed motors, which means high-speed power measurement is required. More or less as the motor fundamental frequency is increasing. As motors just generically go to higher speed, as we can go to higher voltages, we can go to higher speeds. We're seeing an increase in motor pole count for a variety of reasons. And we're also seeing an increase in motor phase counts. This is in both automotive and aerospace. And for all of these reasons, to get the higher speeds with the higher pole counts, with the increased motor phase counts, we need to go to a higher fundamental frequency. And for those of you who don't know, measurement accuracy for electrical power is dependent on fundamental frequency. And actually, this fundamental frequency accuracy typically gets lower as the fundamental goes higher. So it's quite an interesting phenomena, especially when you start looking at filters and all kinds of other behavior of measurement equipment. So when you go to select an instrument, specifically for power, you really need to consider the instrument accuracy across the frequency range. One method we see to overcome this issue of the high fundamental frequency, and I kind of made this slide out of order, but let's start with down here. So this is an example from a calibration sheet where we're actually calibrating for 0, 50, 100, 500, 1 kilohertz, 5 kilohertz. And you can see the tolerances kind of steadily increase because it's getting more and more difficult to measure power at those higher fundamentals. One thing, again, many of you might not know is that traditional power measurements are usually made with a phase lock loop-based system, which is quite slow and also tuned for grid frequencies, 50, 60 hertz. So if you have this phase lock loop that's looking for 50, 60 hertz, it's really going to struggle at 100, 500, 1,000 hertz. So the HBK eDrive system uses a cycle detect method with our real-time algorithms. So we actually filter the current or voltage, pick your favorite signal. We identify zero crossings, and then we average all the signals for electric power, for RMS values within each one of these time periods. This gives you a really high resolution measurement because you're averaging all these samples. And it also makes it very dynamic because as that frequency is changing, you're tracking the frequency. And this is very robust as you go to high speeds, as you go to high fundamentals. As you can see from the values we have in our tolerances and our measured values, they're quite similar across the range. So the cycle detect allows you to be accurate at the high fundamentals because it's not looking for 50 or 60 hertz. So if you really want to confidently measure the power in high-speed motors, you need to make sure the cycle detection method, because electric power requires you to have the right time period for averaging. You need to be really confident in that averaging period for high-speed motors. The accuracy is dependent. Also, there's a whole thing I could talk about filters. We have some YouTube videos and some other webinars. If you're interested, well, please contact us because filtering for power at high speed is also extremely interesting. High-speed torque measurement is also quite difficult. As you go to higher speeds, you end up in this interesting scenario of you need something to withstand that high speed, so you need really high stiffness. You also need a high sensitivity, and those things are at odds with one another. So measuring torque at a high speed is actually quite difficult. You also have the issue of the sensor inertia. The sensor is quite heavy at high speeds. It can actually throw off the dynamics of the system. I'm an electrical engineer by nature, so springs are a little bit of a mystery to me, but you end up with this like spring issue. So HBK does offer titanium sensors that go up to 45,000 RPM. We actually have a high speed series. Because this is quite difficult, we actually go to a different material in titanium to lower that inertia to get that stiffness but sensitivity. There's also the issue of high speed of most torque sensors are strain based. You actually have radial acceleration, so the sensor's pulling itself apart and it's pushing on those strain gauges. Radial acceleration actually will affect your strain measurement. And so what we do is we actually compensate for that at the higher speeds. So we have the titanium, we have that high speed compensation. And the last thing, when you're selecting a sensor for high speed, if you're doing steady states, this is not as important. But if you're looking for like transients at high speed, so you're applying a load step or you're applying a speed step, you really want to look at the bandwidth of the sensor. If you're at high speed and you apply a transient, you might actually miss that if you have a really big filter on your sensor. You might miss it at low speed if you have a big filter on your sensor, but especially at high speed. So check the bandwidth. HBK offers 6 kilohertz of bandwidth. Again, we have some really nice webinars on measuring torque ripple and dynamic torque if you are interested. But mechanical power must also be considered at the high speed, especially under the transients. So you don't want to be damaging your sensor or getting an incorrect reading because the thing is pulling itself apart. For greater phase counts, and this is a little bit of an asterisk in that, the eDrive system does offer the ability to really easily add really high phase counts. So we can measure up to 51 power channels in one location. We have a nice software where you can set up multiple inverters, high phase count inverters, and graphically see that. So within one box, we can take all those phases. We give you really nice software to view that, and we actually set up all the power equations in the background. So you don't end up time aligning systems. You don't have to set up your own equations. So you can really easily measure these high phase count systems. And lastly, electric power is really, the accuracy on it is a mystery to a lot of people because it's honestly quite a pain. You have 4 factors that influence your power accuracy. You have instrument range, instrument reading, motor frequency, like we just discussed, and the phase between voltage and current. So HBK has supplied a measurement uncertainty tool for both mechanical power for your torque sensor and for AC and DC power. Basically, you enter what your the range of your amplifier is. You enter the frequency and you enter the phase, and we tell you what the uncertainty will be. So this gives you the ability to be quite confident, again, at these high frequency measurements, these high fundamental measurements, that you at least know what your uncertainty is. So as it's creeping up, as you're going to 1, 2 kilohertz, and that uncertainty is getting larger, you can at least quantify what it is very easily, accounting for things like the filters you're applying, accounting for the bandwidth of the sensors, accounting for all of these things that go into uncertainty, this tool takes care of it very easily. So if you are really overwhelmed by the prospect of calculating your measurement uncertainty, I know I typically am, we make a nice tool for it. So dynamic power measurements, this is the drive cycle side of it. And I think this is quite an interesting trend. So we are seeing more and more companies stop caring about static power and start caring about what is the energy consumption, what is the efficiency over the drive cycle. Drive cycle being a standardized, typically 30-minute procedure where it gives you a speed for each period in time. So blue on my graph is speed, acceleration is deceleration, stops, starts. It's really kind of like your highway and city miles. If you've ever purchased a car and you get that window sticker, this is where those numbers come from. And then you have a torque that's actually based on what the vehicle's aerodynamics and all of that are. So there's issues with this, kind of alluding to the previous part. Frequency of a drive cycle is constantly changing. There is no fixed frequency. So phase lock loop based systems are constantly looking for a frequency and they're not finding it. So if you're not using a cycle detect method, you're just constantly getting wrong answers. There's also the issue of going to quite high speeds, going to stop, and really having the accuracy across that frequency range. So understanding, am I accurate at the low speed, at the high speed? So there's that element as well. So it actually is a quite challenging measurement issue, especially if you're taking this drive cycle and looking at something like losses. So there's a bunch of different colors here because this test was run under a bunch of different scenarios and different motor control techniques. But it's basically looking at what are my losses. This is the WLTC is a 30-minute drive cycle. What are my losses instantaneously over 30 minutes? Really trying to identify P out minus P in, power out minus power in. What are the losses at every point in time? So I can start identifying these peaks, like my one in blue here, and choosing a better control methodology that lowers those losses. So this is actually quite interesting because you can start comparing different control techniques, pick different spots for different places, and minimize those losses. So you need really accurate power measurement dynamically to be able to identify these loss areas. And then also, tracking temperatures, bringing that in and tracking magnet temperatures and special equations are also things that this was all done with the HBK power analyzer. So another issue is if you're recording data on a drive cycle, you can accumulate quite a bit of data. I mean, a 30-minute drive cycle at, let's say it's a megahertz, adds up to quite a bit of data. You can create quite large files. I just mentioned, if you're looking at a differential, you do need a high accuracy because if you're looking at test 1 versus test 2 and there's a 0.5% difference, you need to be accurate to less than that. And again, phase lock loop based power measurements require a fixed frequency. They're tuned for that 50, 60 hertz. So you want to make sure you have a methodology that is quite dynamic. So dynamic power measurements are needed. So looking at an algorithm like cycle detect, it is quite effective in the transient. This is an example of a motor starting up. So we're in a vehicle, we're at 0 speed, we're out in the field, we start, the inverter kicks in, we see currents, and this black square wave is my cycle detect. This is my calculation period. And we're tracking that really, really closely as the motor's speeding up, as the amplitude's changing. You have confidence you're getting an accurate result. So we're averaging power, reactive power, apparent power on this time basis. And down in the bottom, we see our what I call our power scope, where we can actually see that the power cycle by cycle while this motor is accelerating. We can actually follow our motor control. We can see where we have overshoots. We can really understand in great detail how this machine is operating and then understand, can I tune this point here to lower my losses? So understand losses and controls accurately during transients is a real benefit of using an appropriate measurement period. And another benefit of using certain tools like the HBK eDrive is that the eDrive system takes instantaneous values at a megahertz because you have the switching frequency. You have to measure at a really high frequency. You have to measure at a really high frequency, hundreds of kilohertz to megahertz, to get an accurate measurement. So if you're measuring for 30 minutes at 12 channels. It's something like 50 gigabytes of data with an 18-bit measurement in. Might be a little off, but that is a significant amount of data. If you don't want to store all that, the tool like eDrive uses some data reduction techniques where every half cycle we're calculating that value, and then we're storing that value, and then we can throw out all of the other data. So you can store just those calculated results and reduce your data file size from gigabytes to megabytes. So it's a really powerful tool, and that's because we calculate everything in the real time. So we're calculating everything in hardware, and then we're just storing those results, so you're not filling your hard drive up. So by doing those cycle-based calculations, by just storing that cycle basis, and all of that megahertz is going into that calculation, and then we're not storing it. You're able to turn that megahertz data into calculated power RMS results that you can store. So you're able to just calculate at, let's say, kilohertz rate. And you can do this for days because the data rate is so low. And we do have people doing durability tests who are running tests like this for like 80 days, 2,000 hours. And you might say, well, what if I want to store that data? There's triggering options. But what you end up with is you have that high frequency sine wave of voltage and current that you see in red. And then you have that time averaged RMS that you're just storing at the kilohertz rate. And you end up with your power, reactive power, apparent power, also stored at that low rate over your drive cycle. So you can store your whole drive cycle, you can store the raw data if you want, or you can just store the slow rate data. So we make it very easy to reduce the data. So you can drastically reduce file sizes or store all of that data with clever techniques like the cycle basis in the real time. You might be asking, Mitch, for the dynamic power, you're talking about dynamic power. Why don't you just multiply V times I? Great question. Instantaneous power is at the switching frequency. You have this inverter. So if we look at our voltage in blue, current in red, we have a high frequency thing in red, our current. We have a really high frequency thing in blue that has these switches, the inverters here. And then we have our calculated power in green. And we can see we have negative power swings. We have power at the switching rate because we're multiplying point by point. So instantaneous power is at the switching frequency. This is why we can't just take V times I. It's useless. We need the correct averaging period, especially to get an accurate result. It's very hard to determine the accuracy on this instantaneous because it's negative, it's positive. When the average is 32, you're getting 150 and negative 32, and it's just outrageous. So it's really not useful for understanding the power flow losses or controls. You might say, I don't need all that accuracy. I just want to know my dynamics. Here is a very cool thing that HBK has been doing. And we have a scientist who spends a lot of his time figuring out how to understand the accuracy of this. So I will start. This is not the most accurate method. Cycle-based is the most accurate method. But if you really need dynamics and you don't want phase delays and you don't want to play around with filters, you want to do it correctly, this is how we approach it. So we measure our line currents and voltages. So in my PWM that I'm circling with my laser pointer, that's the voltages, and then we have our currents in the blue, orange, and yellow, the sine waves. And rather than doing a cycle detection on the currents, now we're going to go look at the voltages, and we're actually going to look at the PWM switch, and we're going to cycle detect the switches. And we're going to average over 5, 10 switch periods. This is happening in milliseconds or less, and it gives us a really good time basis to average, where we can say this has a level of accuracy. We're still working to quantify it, but it's very dynamic and it eliminates that high frequency and without a phase distortion. So you're not looking at a filtered version. You're not looking at a phase distorted version. You're looking at a really, really good accuracy from what our numbers are telling us initially. Non-phase delayed version. And let's look at an example. So we can see this purple sine wave is cycle detecting our switches. So 10 switch cycle average. We're staring at that voltage. We're tracking that switching frequency. And if I'm not talking sense, ask me offline if you're interested. And what we see is I have my current in blue, and we can see something happens right here where we get a real change in amplitude. And if we look at the cycle-based power, which the cycle-based power is still dynamic, but it has this kind of phase delay. And we also see that, you know, it takes, it misses a lot of the dynamics. What is happening right here? Well, my yellow sine wave, or my yellow trace, is a switch-based. We can see that power inrush. We can see how the motor control handles that power flow, and we can see that average out to the same value, but we get all those dynamics. So you might say, like, what's the accuracy? We're working on it. But it's super dynamic, and where we miss a lot of things with the cycle detection in the transient, we catch that with the dynamic power measurement. So the cycle detect is still good for drive cycles. It's still good for long periods that are more gradual. But if you really want to dig into like transient power and transient, how it reacts in the transient, this cycle based or this switch cycle based power is incredible. So we're very excited about this. This is something, again, we can discuss offline if you want to look at implementing this. All right, next topic, flux measurement and torque estimation. So we're seeing an industry trend, and I think people have been doing this for a while, to really calculate the flux and really evaluate what your torque estimation is. And people are starting to think use flux a lot more. So torque cannot be measured directly in a vehicle, not practically. But flux can be used to estimate torque. And you know, we've got our equation here, and I'm sure somebody will hop up and tell me I wrote it wrong. And you might say, what is flux? Well, it's magnetic strength or the flux linkage is the magnetic field going through an area. So it's how strong is my magnet. So flux cannot be measured directly, not in a motor, not really effectively. And flux is loss and temperature dependent. So it makes it quite difficult to do in a vehicle without a lot of thermocouples, without a lot of knowledge of the states of the system. My other fun fact about flux is that everyone seems to have their own method of calculating flux and estimating flux, you know, using different manipulations of the equations. And many times we're seeing lookup tables used. So flux is difficult to calculate accurately. And this is where I think HBK has done some cool things to help. So we look at the technical implementation. You know, you can go through some equations and you can kind of look at some math and figure out, you know, what your flux is. And from a measurement standpoint, we measure voltage and current, V and I. We can look at temperature to estimate resistance. Or in a measurement test stand, we can use mechanical power to assume rotor loss and assume loss and kind of manipulate this equation. There's some clever stuff. We can discuss that. And then we have the speed of the unit. We can rearrange these equations to get our flux. So a basic example is, you know, lambda equals V minus losses over speed. And what we end up doing is doing, you know, DQ0 calculations for voltage, DQ0 for current, which I have displayed here. Our software can calculate that in the real time and display that as a scope trace. So flux can be calculated in many ways. So we look at a motor flux example. I just implemented that simple equation. I know you're probably not using that. But we measure the three-phase voltage, we estimate the resistance, we execute the DQ0, and we calculate flux. And we can see our equations here. These are all implemented in the hardware in the real time, available for feedback to our hardware in the loop. And then we have our example. So we have torque. Torque is constant, and we're sweeping speed. We have our voltages in blue, our currents in red, our IQ in other red and maroon. We have our VD/VQ in blue and other blue. And then we have our flux D and our flux Q in green and purple. And in the real time, we can view that as a scope trace. And you can see the flux as we're ramping up and really understand those changes as they're happening. So we can start to understand our control and start to make things like flux maps very easily. We don't have to take a scope, make a measurement, go to MATLAB, process, then understand. You can have your efficiency and your flux in the same place. So we offer custom calculations. You can enter your own proprietary flux calculation. It's going to be time aligned to torque because we're measuring that on the same timestamp. And then if you want to use temperatures, we can also bring in your resistance, your temperature for doing that loss estimation. So we give you a lot of flexibility, but with high accuracy sensors, with high accuracy amplifiers, you can get a very high accuracy measurement of your flux. And we do have some cool methods for calculating flux on our own that we can implement if you want like something to compared to. Now, the other thing we're seeing is the controller is calculating torque on its own. You know, it's calculating flux, it's getting to torque eventually. So we can compare measured values to the controller estimation by measuring the CAN bus of the system. And now you're getting your voltages, your currents, your torques, your fluxes, and your calculated torque, your calculated ID, your calculated IQ from the inverter. Play that in all place. So we can measure the CAN on the same timestamp, compare that to your values. You can look at what that difference is and start to calibrate your torque estimation. And here's an example. We have torque command in black, real torque in pink, and the torque command doesn't actually get to the controller until this point. And then we get this nice, kind of estimation. This is an experimental controller, so it's way off. And we can also do that for our RMS values. We can do that for any value in the controller and in the high accuracy calculation. So calibrate your controller and lookup tables with time-aligned CAN. And the calculations happening in the real time. All right, measuring harmonics, one of my favorite topics. So motor harmonic measurements, we need harmonics and we hate harmonics. They're good, they're bad. But sometimes we use controls to inject harmonics. We do this to achieve higher voltages. We do this for torque ripple suppression. And we do this so we can treat the motor as a position sensor. But the thing is, harmonics also contribute to power. This is harmonics of the fundamental. Contribute to power and losses. So accurate measurement of harmonics is needed for control and loss characterization. We need to understand these. So inverter-driven systems have a fundamental harmonics and switching harmonics. Those are two different things. Most of what I'm going to talk about today is the fundamental. If you measure high enough, you can also do these things with the switching. Harmonics of the fundamental carry power and power loss. If you filter out your harmonics, you will get a wrong power value. I can assure you that. Harmonics create torque ripple and mechanical vibrations, so we're seeing a lot of value in measuring those in the same place. And harmonics can be calculated in many ways. FFT, static calculations, dynamic calculations, order-based calculations. If you look into the NVH world, there's 1,000 different ways to look at frequency content. So there's many different ways. And here's an example of a current, a accelerometer, and a current, a torque, and an accelerometer all measured in one place and then shown as an FFT. And again, this is using our software. You can look at all of these things in one place with one time-aligned stamp. So FFT, I'm going to fly through this. We allow you to view as a simple FFT. This is a quick snapshot. It's kind of a gut check. This is something that can be offered in the real time. You can view fundamental frequency and harmonics, just kind of see your first, your fifth, your seventh. And then you can view your switching frequency and its harmonics as well. So eDrive offers a simple FFT. I don't personally like looking at FFTs. What I much prefer is looking at things more of an order basis. So here's an example of a sine wave. And then we do a order-based calculation where we actually give you the amplitude, the frequency of each harmonic up to a given value. So you can say, I want the first 50 harmonics, and we give you the nice little bar graph showing the first 50 harmonics. You can understand how the harmonics are with respect to the fundamental. You can view the signals as a percentage of the total, and also view the signals as a bar graph. So you can really look kind of visually at two different control strategies, understand what's happening. So this is something that's possible in the eDrive to do that order-based harmonic analysis. This is really cool. Now, my favorite one is tracking harmonics in harmonic phase. I've alluded to this a few times now, and I probably should have included it. But if you're running at 1 kilohertz and you have a 3 kilohertz filter, you are missing your fifth harmonic. And your fifth harmonic carries power, carries negative power. So you're actually going to see a higher value than what you actually get. So if you have your filter set high enough, you can start to do things like looking at your harmonic RMS and phase. And this is an equation we offer in the eDrive system. And I have my calculations up here. We look at the fifth harmonic of voltage, fifth harmonic of current. We look at the phase of both of those, and then we can calculate power because we have voltage, current, and phase. Cool. So what I show in this graph here is on that dynamic basis, on that cycle basis, we are looking and saying, okay, here's my amplitude of my fifth harmonic voltage in blue. Here's my phase in black. Here's my amplitude of fifth harmonic current in red. on the cycle basis. Here's my phase in black, and then here's my power, and it's bouncing all over. But if you have the right accuracy and you can trust, this 5 watts in your measurement uncertainty, this is an awesome measurement, and you can start to characterize your harmonic losses. You can look at your harmonics during transients. You can do all this cool stuff to analyze your harmonics, your harmonic losses through things like drive cycles. Again, we're doing this on the cycle basis. We're doing this in the real time in hardware, and you can track those individual harmonics. You can track those harmonic injections all dynamically. So it's really cool. You don't have to go to MATLAB. You can do it in your acquisition equipment. So eDrive can measure the harmonics and understand those injections and losses without going to MATLAB, without getting a scope. You can do this all in your power analyzer, one piece of equipment. Electromechanical system measurements. We are seeing a big push for noise and vibration measurements and noise and vibration analysis in electric machines. I was actually at a university doing some really cool work today in Tokyo. But long story short, our inverter makes a high frequency voltage. The motor filters that to a high frequency current. We saw this signal earlier. The motor rotor filters that current into torque and speed, but that's got dynamics. It has torque ripple. And the radial forces, the torque ripple, the magnetostriction of the machine, excite the housing and create vibration and noise. So that inverter has a big effect on that mechanical system. If we change that inverter control, we change that mechanical system. Again, I showed this image earlier, but torque ripple is hard to measure because of sensor accuracy and bandwidth. Time alignment between electric torque and vibrations is needed to understand cause and effect. If I change my inverter control, does my torque change? Does my vibration change? And then inverter control and dead time and phasing can affect noise and vibration. So again, we want to understand these things. We want to understand when voltage, when current, when torque, when vibration, how these all correlate together. So you need a common timestamp, you need signal alignment, and then you can start doing your analysis with confidence. All right, the eDrive system can measure all of these different signals, AC voltage and current, noise, vibration, CAN bus, all into one measurement unit. And we can do lots of them. You can also bring your high accuracy, high speed torque in. So you can see voltage, current, torque, noise, accelerometer, microphone, all time aligned, so you can have that confidence. You can go to that FFT, you can go to that cycle-based tracking. Now an example. This was, again, a fixed torque. This is actually the same example I showed earlier. I only have so many. So I do a lot of things with each one of them. We have our torque in pink, we have our speed in green, we ramp speed, we're bringing in accelerometers, and we're looking at our voltages and currents. And if we zoom in on that torque, we can see we got kind of normal torque ripple, and then boom, we hit a resonant point. We hit a resonant point, and there's more than one. So we're doing that speed ramp with constant torque, we're measuring power, we're measuring torque. And if you're taking average power, you're averaging over a period, even the cycle period, you might miss this torque because cycles are synchronous to the machine rotation. Torque ripple is synchronous to the machine rotation. If you average torque over rotations, you're averaging out that ripple because it will average out to an average value. So you want us to understand torque ripple, you really have to be looking at it. But once we start understanding torque ripple, we can start understanding its contribution to noise, start understanding its contribution to vibration, and understand how to mitigate it through our motor control. If I tune this inverter, it doesn't change, So we can measure all of these things on the same timestamp: voltage, current, accelerometers, torque ripple. And here's a color map, where you can just take a color map of your voltages, currents, and again, torque. And we see this has a 340 hertz resonant. We see our 48th, our 24th, our torque ripple orders coming through. So current, voltage, and torque ripple affect noise and vibration. So we're seeing this trend. We're starting to see motor people work on NVH, which the NVH people think is crazy. We're seeing NVH people work on motors, which the motor people think is crazy. And I always push, guys, please measure voltage and current, accelerometers, and microphones at both, so you can really start to understand the system dynamics. Because you can do a ton with inverter control to minimize your noise and vibration. All right, test acceleration. We're seeing an industry trend for an increased number and an increased density of efficiency maps. These maps are used to tune our controller. These maps are temperature dependent, and we end up needing different maps for every temperature, every battery voltage, different controls. We end up having tons of maps. And we're seeing another trend towards more density in the efficiency maps, which means more points of resolution. And then there's other tests as well. And what we have is, you take a torque and speed, measure efficiency, torque and speed, measure efficiency, and then you get this contour. And because of the number of maps, because of the number of points, and we're seeing people go to 25 maps or so, wanting to go to more. We're seeing people go to, thousands of points. They used to do hundreds, now they're doing thousands, and this can take weeks. So what are some sources of delay? And I won't read through all of these points, but you're making a lot of measurements with different data types, different numbers of channels, different alignments, and this is taking time to process. I've talked about cycle-based measurement. If you start measuring on weird periods for different instruments, you start seeing wrong results. If you start filtering poorly, you start seeing wrong results, and you end up ghost hunting because of your instrumentation. If you have errors, if you set a filter wrong, you might need to rerun tests. The machine heats up and it needs to cool down. We do these efficiency maps at a very fixed temperature, so you end up waiting on thermals. Each measurement point takes time, and when you're doing thousands of points, seconds add up. And then troubleshooting. Nothing ever goes right the first time. So there's many sources of delay in motor testing. Let's look at a case study that we did. We have a 9-second per point reduction. So we looked at a phase lock loop based method that takes 10 seconds per point. And then we looked at a cycle detect, which we put at 1 second. We could have done it faster, but we decided to do 1 second. And because of the thermal stuff, because of the transition periods of the dyno, we wanted to look at it rather than just saying 9 seconds per point, really look at what that would be. So we had 5 temperature states, 5 battery voltages. We had 25 maps. We did a 1 second measurement with cycle detect, a 10 second with the phase lock loop, and then we looked at the transitions. It was about 5 seconds per point, and then heating up and cooling down about every 100 seconds. We had a cool down for about 100 seconds every 60 seconds. And what we see is some pretty significant for 200 points per map, and at 25 USD per day, 2,500 USD per day for doing a testing house, you end up with about 17 grand in savings for that test at 200 points per map. You go to 2,000 points per map, you end up with about 117K, and that's just the testing house. The time savings is huge too, 600, 500 hours. That's really significant. So we're seeing really significant savings in time. We're seeing really significant savings in the number of test points, and we're seeing significant savings in money. So these are things to consider. And we offer feedback to automation systems. Because we do all our calculations in the real time, we can feed answers back to the automation system at 2 kilohertz. So as soon as you have your measurement, you can move to the next point, measure the next point, measure the next point with a really nice handshake where we can feedback over EtherCAT CAN API at up to 2 kilohertz. And we can receive start, stop, trigger, change range, change reading over CAN, EtherCAT, LabVIEW, Python, or .NET, C#. We have an API. So real-time calculations and feedback allow for test automation so you can test at the fastest rate, so you can save more time and more money. All right, and I think I'm closing out on electrical noise and high voltage, and this one I'm particularly excited about because we're announcing a new product. So we're seeing an industry trend for higher voltage and faster switches. We're seeing up to, right now in automotive, 1200 volts, 800 volts is becoming quite common, but these silicon carbide switches are just snapping extremely fast. And we're starting to see GaN as well. So we're looking at the high voltage safety, like from the human perspective and from the equipment perspective, this is terrifying. And we really, I put this picture up here. This is our equipment. This is at a customer. I mean, this is the kind of thing that's not uncommon. This is not a one-off. This is a lot of people. This is not just our equipment. This is how these labs look because there's so many cables. If one thing gets stripped or one thing gets cut, you've got 2,000 volts about to be a bomb. So high voltage safety we look at is really important. These silicon carbide and GaN switches are fast. The rise time is like nanoseconds. So what you end up with is a really high change in voltage in a short period of time. You have a high dVdt. Everything looks like a capacitor, which means everything carries a current. You're getting electrical noise everywhere. Every cable is an antenna. They're really hard to measure from an electrical noise perspective. And per my picture, cabling can get quite complex, and a lot of mistakes are made just because of cabling. So new powertrain demands are difficult to measure because of the cabling, because of the fast switches, and because of the high voltages. And a typical test setup ends up looking something like this, where we have copper cable coming into an instrument, current sensors, copper cable to a power supply, copper cable to the instrument, torque and speed coming over copper, and then things like temperatures coming over CAN bus. This requires long cables, copper connections, which couple noise. You can put the instrument close to the measurement unit, but is that always practical? So, what could be better? What could be better? Well, what if we had a box that did all the digitization sitting right next to the machine? What if we had high voltage modules that were completely floating, sitting next to the machine, digitizing, and then connected to the measurement equipment over a fiber optic cable? What if the current sensors plugged into that fiber optic box, or that completely isolated box got digitized and got sent back over fiber optic cable? This is the future that we're looking at. We're coming out with what we call our satellite modules. We have voltage satellite, which is 4 voltages, and a current satellite, which is 4 currents. And the goal is to shorten those cables to be, like 10 centimeters, as short as possible. So we have less distance to be coupling that high dVdt. We have less copper cable to make it confusing. 4 voltages come into voltage box, 1 cable back to the unit. 4 currents come into the current box, 1 cable back to the unit. Really try to shorten those measurement cables, bring everything back to 1 common cable. And then from the electrical safety, we don't have a copper cable coming back to a control room. We don't have a copper cable coming back to across the lab. That 2000 volts is 10 centimeters. And then it's fiber optic. There's no copper connection. It's safe for people. It is safe for the equipment. Uncompromised safety. You are not putting people near high voltages. EMC issues will be minimized because of short cable lengths and everything being fiber optic and eliminating, extra copper cabling. High accuracy due to shorter cables and less reflections. That's the thing I didn't even touch on. There's going to be reflections from these silicon carbide that makes life absolutely a nightmare from a measurement perspective. Shorten your cable length, you shorten your, I don't know if you remember your physics, you shorten that wavelength, you don't get that bounce. Integrated power supplies, and you can put these up to 500 meters away. You can just have these boxes sitting in rooms and flip cables around. So specs, I'm super excited about these, as I'm sure you can tell. I'm excited anyhow. This is extra exciting. Plus or minus 2,000 volts. We're getting ready for the future. Voltages are only going higher. Safety is only more important. Up to 20 megasamples per second. We really, for power, it's all in the fundamentals. So high switching frequency doesn't really matter, or high sampling rate doesn't really matter. But as current sensors get more mature, we start to need more and more for the powers. Fundamentals go higher. Also, if you want to look at your dead time, again, you get that scope functionality. You can start doing analysis with the high sample rate. For individually replaceable voltage channels, if you have an accident, blow one out. Nobody's going to get harmed. Swap that out. And they're also really, really good isolation. It's an incredible measurement from the differential standpoint. And we have all of the CAT ratings you can get. We have the 1500 volt DC rating. We have the 1000 volt Cat 3. It's really fantastic. Current satellite, more or less the same, except now we have a potential integrated power supply with 6 ranges. Power accuracy is going to be untouchable. 0.015% of reading plus 0.02% of range, and that is going to be real nice across the frequency spectrum. Same or better than our old equipment, but with all the safety and the high sample rates. Highest safety ratings, shortest cables, best signal integrity, industry-leading power accuracy. This is going to be the end-all solution for channel modules. And you can stack a bunch of these together. And in the future, we're also going to have temperature modules over fiber, torque and speed over fiber, NVH over fiber to really just have a completely isolated system. This is going to be the be-all and all of measurement. I'm so excited. So in summary, eDrive testing, future-proof. We make a lot of measurements. We're coming out with things like fiber optics. We allow you to put in your own equations. You can bring in electric and mechanical. It's a really powerful system for understanding the system. Accurate and dynamic. we have really good accuracy. We are going to have even better accuracy in practice when you start looking at the noise immunity. And we allow you to do things like drive cycles. We make sensors, we make software, we make acquisition, and we have expertise. You can come to us and we're one throat to choke, as a colleague of mine says. Auditable testing, we record everything if you want it, or you can throw it out. But we can record electric, mechanical, torque ripple, all in one location, all in one timestamp, in one data file for a very long period of time. You can store as long as you have hard drive space. So thank you. I think I've gone a little long. I'm very excited for your questions. I'm Mitch Marks. You can find me on LinkedIn here. And if you want more information on eDrive, you can find that with this QR code. Please just scan this with your phone. I'd like to thank everybody at Charged for having me. It is always a pleasure, and I look forward to speaking with you guys. Thank you for attending Motor Testing Bouillabaisse. I went through a lot.